and see what questions you have on that. All right, we had the derivative rules yesterday. Of course, we have still have our power rule. We have the derivative of e to the x. We have b to the x, so a different base. We worked a few examples of that. We have our log derivatives. And then we had all the trig derivatives. Now, on our next quiz, this is going to be a small piece of this. The doing the derivatives would be a very small piece. I think on the last quiz, out of 44 points, I think there were 4 points plus maybe a few here and there where you had to do it inside of another problem, but they were pretty simple ones. Okay. Same thing is true here. After Thanksgiving, we'll be working on these derivative rules in great detail and be really working hard on those. So right now, this isn't going to be a huge part of it. So we don't want to get too hung up on it. But any of those you want to see? Number 20 on page 139, section 2.6. Okay. So number 20 says that f of x is equal to, what is it, 3 log base 2 of x. Is that the one? Is that the one we're looking at? Okay. So you had to do f prime, and I told you didn't have to draw the graphs or anything for this. So on 20, you were looking for f prime of x. And so when you have a number out in front of a derivative, it just hangs out there. The derivative of this is 1 over x times 1 over ln 2. And that just comes straight from this rule right here. Log base 2, 1 over x, 1 over ln 2. Okay? So that's f prime. So then problem was at, what was it, 26? 26 said do f double prime. All right, now what I would do, I told you when you do your derivative, you don't need to rewrite them for me, rearrange them. But to do the next derivative, it might be nice to do that. So probably would have been useful here if I would have said, you know, this is just a number. 3 is just a number. And it's all multiplication. So let's move this 1 over ln 2 over here. So it's like 3 times 1 over ln 2 would just be 3 over ln 2, right? That'd be 3 times 1, you know. So this is really just 3 over ln 2 times 1 over x. Now, you might also be saying, well, yeah, couldn't you multiply that together and get 3 and then have the x on the bottom? Yes, but I think that makes it more confusing. I think to separate out my number and my function with x, I think is preferable. So I think writing it this way is best. And so some of you make it harder on yourselves because you don't either don't rearrange things properly or don't know how to rearrange them or get confused and rearrange them. If you can rearrange them properly using just basic, you know, multiplication algebra rules, you will greatly help yourself be able to do the derivatives. Okay, now these, I even think these are going even a little beyond what I care to have you do this next quiz. Okay, and if there is one, it'd be one problem worth a couple points, and that might be all there is there. Okay, so I'm not getting too hung up on it yet, but we want to begin to understand what's going on. So I'm putting those together and just having this. Okay, now when I look at doing the derivative of this, I think, does this match any of my rules? What do I need that to look like? X to the negative 1. So I really should even rearrange it a little more. So I should make this 3 over ln 2 times x to the negative 1 is what I should do. Okay, so now I'm ready to do it. This is just a number setting in front. So it just hangs out there, and now we just bring our power down in front. So this one's going to be a negative 3 over ln 2 times x to the negative 2. Right? That would then be it. Now, maybe the back of the book makes it look a little different. It might have flipped that down to the bottom and had an x squared down there maybe. Okay? All right, what was 32 then? Did you have to do that? Was that like an or you didn't have to do that? We didn't have to do an antiderivative? Okay. Okay, good. All right, that's fine. Okay. Looks like that. Yes, Cody. 16. What'd that one say? Yeah. Now, I kind of like how the book does this. You're never going to see a function like this in your life other than right here. But what it does is it really makes you think about the rules. An exponential function is when you have a number raised to an x. And those have special rules. Those are these right here. Okay? A number raised to an x. But x raised to a number is the power rule. So it's very important that you say, I put these on the same page for a reason. X raised to a number is the power rule. A number raised to an x is an exponential rule. Okay, an exponential thing. And so they're very different. So when you do the derivative here, this is an exponential. It's its own derivative. When you do this derivative, you bring the number down in front because e is just a number, and then you drop the power by 1. And then the derivative of a number is 0. The derivative of a number, because that's what e is just a number. So e is a lot different than e to the x, right? E to the x is a function. E is just, e to the first is just a number. Okay, so that's the first part. And then number 22, you had to do the next derivative. Okay? And so the derivative of e to the x is still e to the x. Now what you have is a number out in front. Well, that just sits there. And then you bring this power down, so that's e minus 1. And then it's x raised, and then you drop that by 1, that'd be e minus 2. And then you can just leave it just like that. Okay, so you got a number set in front, it just sits there. You bring this down in front, and then you drop the power by 1. And that's good enough right there. Did you have to do an antiderivative on this one? What number was that? 28? So on 28, we're doing the antiderivative of this one up here in blue. Okay, so what's the antiderivative of e to the x? E to the x, that's easy. Okay, what do we say for our power rule? We raise it up 1, and then divide by that new power. So that'd be x to the e plus 1 over e plus 1. Right? That's what we said the antiderivative of a power is. We raise it up 1. Like if we had x cubed, we raised it up to x fourth and then divided by 4. Okay. Not what I heard, but that's okay. I was hearing, were you applying for a job at Qdoba? That's what I heard. Anyway, all right, just kidding. So we raise that up to e plus 1, divide by e plus 1. All right. Plus e. Now what's the let's pretend that was a 7. What's the antiderivative of 7? Antiderivative. 7x. Right? 7x. Because the derivative of 7x is 7. Right? The antiderivative of 7 is 7x. So what's the antiderivative of e? No, not e to the x. E times x, right? E times x. That's different than e to the x, right? It's e times x. It's just like a number, like 7x. And then, don't forget, we usually put on a plus c. Remember we said when we're doing an antiderivative? A lot of times, we should put on the plus c. And that's just the shift. That's just that vertical shift. Because we don't know. Because again, if you check this by doing the derivative, there could have been some constant here. When you did the derivative, it just became 0. Right? All right. Again, that the antiderivative part's not going to be a huge emphasis. They're going to be pretty simple, straightforward ones. These were a little tricky, but they served a purpose. They were tricky in the sense that we wanted you to really have to think about the rules here. Okay. All right. Anything else? Okay. So, like I said, I've got somebody to still take the test. The grades are online. If you do want to come in and look at them, and can find me sometime, like in the morning, probably the best time at lunch. I can show it to you, probably here. Anyway, you can see how you did. So, all right. Well, if that's it, then let's go ahead and get your notes out, and we'll go ahead and talk about a couple of new concepts here. They're a little bit disjointed. They don't really connect. I mean, they all involve derivatives, but other than that. But once we get past today's lesson, most of the new kind of stuff that we're going to add here for the next quiz will be added. I mean, we'll have talked about it. It's just going to be a matter of really digging in and working on it on your part, and then seeing where we have questions and clarifying things, before next Tuesday. All right. So I've got 4 things here that are 4 main concepts we want to have for this next quiz. You notice 2.4 is kind of included. It was included in the last quiz. It's kind of included in this quiz because there's a piece of it we didn't really talk about yet. So I'm going to run through these 4 just real quick, and then we'll start writing some stuff down. Okay. The first one is a new concept, something called differential equations. Differential equations. All right. We're going to hit that first. The second thing is global max min. Okay, that's also kind of a new thing. We've talked about that term a little bit, but we haven't really done anything with it yet. So global max min problem. So we're going to get into that. Okay, the next thing is chart stuff. Now that we did do. Increasing, decreasing, concave up, concave down, local max min, that kind of stuff. Now we haven't done much with the concavity. That involves a second derivative. But once we get the rest of it down, that comes pretty easily. That we did on the last quiz, but we did it with polynomial functions. Today we're going to do it with trig functions. Okay, we're going to look at some local max mins and stuff of some trig functions. Okay, so that really isn't new, that idea of do the derivative, set it equals 0, do a number line, that kind of stuff. All right, and then the last concept, which we just got to talk about there, is derivative, just kind of those derivative rules, those antiderivatives, a little bit, not much with antiderivatives. Just some pretty basic things. So that's it. I mean, those are the things. Okay, so we need to go back to these first 2 that we haven't heard about here. So let's do this right here. Differential equation. What is that? Well, first of all, let's just write a definition for this. So the definition would be an equation that contains one or more derivatives. An equation that contains one or more derivatives. Okay, now I'm going to give some examples here, and you can put these right in your notes if you want to. I'm going to put them on a separate page here because I want to kind of keep this clean for later days to go back and look at. So before I do some examples, I'm going to put one more thing here. The solution or parentheses S, solution or solutions to a differential equation. We usually abbreviate that DE, a differential equation, DE. The solution or solutions to a differential equation is the original function y f of x dot 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 etc. Now that's the part we really got to think about. That seems weird. We're used to solutions to an equation being what? The solution to an equation, what do you think of as a solution to an equation? Like a number, like 2, right? Well, that's not what this says. This says the solution is a function. The solution to a differential equation is another equation. Okay? So that's the first part of differential equations you got to kind of get over, right? You got to kind of get that through your head. So, an equation that contains one or more derivatives is called a differential equation. The solution to a differential equation is the original function y. So, like the output, if it's y or if it's a y prime derivative that's in it, then y equals is your solution. All right, so let me do an example, or you can put that right in your notes right there if you want to, or on a separate page. You probably make sense to put them right there. So let me give you one here. F prime of x equals 2x minus 7. That's a differential equation, right? What's it take? It needs to be an equation. Is that an equation? It's got an equal sign in it. If it's got an equal sign, it's an equation, right? That's why they're called equations. It's got an equal sign. And does it have a derivative in it? Does that have a derivative in it? F prime, right? F prime in it. If it's an equation, got a derivative in it, it's a differential equation. So, in one sense, we've seen differential equation before. We've seen that many times, right? The solution to the differential equation is the original function, which in this case, the original function would be what? What would it be called? F of x. Yeah, I don't want it yet. What would it be called? It'd be f of x, right? So again, this is where we've got to get over this idea of a solution is a number. A solution to a differential equation is the original function. So here's our differential equation right here. This is our solution right here. So in a way, we've already been doing this on a very basic level. Okay? Now, can we find this original function f? Sure, by doing what? Antiderivative. Matter of fact, you could say we've been solving differential equations all the way back in chapter 1 when I gave you an f prime graph. Remember those? I gave you an f prime graph and asked you to find the f graph. You were solving a differential equation. I gave you a derivative. That wasn't an equation, it was a graph. But that's what you were doing. So in a sense, a basic antiderivative problem is solving a differential equation. Those are the easiest ones there are. Okay, so what would this one be? X squared minus 7x plus c. Right? And you're done. You solved it. Doesn't feel like you really solved anything because we're so used to algebraic equations. Right? I mean, if we put an example over here of an algebraic equation, you don't have to write this down if you don't want to. But if I did 3x plus 5 equals 17, that's an algebraic equation. Right? Now, we spend 2 years of algebra class learning how to solve algebraic equations and into advanced math and trig equations. And we just did a review worksheet 2 days ago on solving equations, right? When you get done with calculus in college, if your major requires you, the next class you would take would be a class in differential equations. You'd spend a whole class solving differential equations, just like you spent Algebra 1 and Algebra 2 and some of advanced math learning how to solve different types of equations. Okay? All right, so we know how to solve this. Now, we learned some techniques. For one like this, we do this. Now, on quadratic equations, we learned about, getting 0 on one side and factoring. With trig equations, we use the unit circle. With exponential equations, we do the log of both sides, right? I mean, we've learned all these strategies of how to solve certain types of equations. Okay? And then we divide by 3 and we get x equals 4. And there's our solution. Okay? Now let's talk about one more aspect of this. In algebra class, a lot of times your teacher would tell you to check your solution. How would you check or verify? I think the word we're going to use a lot in here is verify. How would you verify this solution? Plug plug your solution back in for x, right? Now, if your teacher was really mean and really made you verify, maybe back in the early days of doing this, they might have made you do this, it would really look like this. You would write down your equation. I call it a T-chart. That'll be the term I use a lot of times. So if you ask me, how do we verify this? I'll say, well, this is where you do the T-chart, okay? How do you verify that x equals 4 is a solution? Well, you take your solution and you plug it into this. So you'd have 3 times 4, plus 12 plus 5, 17. Oh, yeah. Check. All right? The two sides are equal. That's what you wanted. To verify, when you plug it in, you need to show that the two sides are equal. Now, I could have given you a harder one. I could have had something over here like 4x equals 9, right? We could have solved it. Then we'd have had to work out both sides of this to show that they were equal, right? We'd have had to plug 4 into this side, plug 4 into this side, and show that the two sides were the same. But that's how you verify. Well, we're going to do the same thing over here. Now, this you might write down if you want to. Verify this one. Verify that this is truly the solution. Well, what we do, now this is always confusing because it's like, wait, I got two equations. Which one do I do with my T-chart? Well, this is why I give you this example. Think back to what you did here. What you did here is you took your solution and put it into the equation you were solving. Well, this is our solution here, the original function. That's what we want to plug into the equation we were solving. So down here you do f prime of x equals 2x minus 7. You do your T-chart right there. Kind of makes a T there. That's what I call it that. It makes a T. I don't know. It's kind of creative. I don't know. It's not very creative maybe. But, so, and now I got to show that these two sides are equal. So I have to plug this in. Well, where can I plug it? Well, there's no f of x here, so I don't plug it there, but there is an f prime. Oh, what's f prime? Let's do that in red. What's f prime? Well, I'd have to do the derivative of this. What's the derivative of that? 2x. What's the derivative of that? Minus 7. Derivative of that? 0. Now, this is a pretty trivial example because, of course, that's a derivative. I got it by doing the antiderivative. Kind of makes sense. We'll do an example where it's a little more involved here in a second. So f prime is 2x minus 7. I get that from my solution. Oh, so I plug that over here. Plug that in for f prime because that's the same. And, oh, yeah, there it is. Verify. So, I mean, that's a pretty easy one. We already said when you do an antiderivative, you check it by doing the derivative. Okay? We got that right there. So let's try one more. Let's try a little harder one. Okay, so let me give you a differential equation. Y prime equals 1 over 2y. Now, is there anything that strikes you about that differential equation? There's what? There's not an x. Well, couldn't y just be the input? No, because there's a y prime. We always do the prime to the output, right? F or the y or whatever. The output variable is in the equation. That happens with differential equations. So we could not do our normal antiderivative rules with this one. We can't. Our antiderivative, you know that d over dx thing we do with our derivative? Says with respect to x. All those rules work with respect to the input variable only. We can't do them with a y. We can't bring this up and make it y to the negative 1 and do some sort of power rule. We can't. It's got a y in it. Okay? But that's okay, because we're not going to solve this anyway. Okay, we're not. I mean, matter of fact, we're not going to hardly solve any of these. We're not ready for that. Okay? It's kind of like your algebra teacher, when you're very first beginning to learn about equations, gives you some equations and says, just show that x equals 2 is an answer. And then you just plug a 2 in and you practice doing it that way. If you take an Algebra 1 book and look at the very beginning of the book, before you start solving equations, that's what they do. They give you equations and they say, show that x equals 2 is a solution. So you plug in a 2 and you show the two sides are equal. We're going to do the same thing. So we're going to have problems where I'm going to give you the solution and then just tell you to verify that it is. So that's what this example is right here. So I'm going to tell you that this solution, and we'll word it differently. Sometimes I'll say verify that this is a solution. Sometimes it'll say, is this a solution? And so you'll just check it, and if it works, yes. If it doesn't, no. That kind of thing. But I'm going to tell you that I think the solution to this is y equals square root of x plus 4. I think that that is the solution, but I want you to verify that for me. Okay? So, what are we going to do? What are we going to write down for our t-chart? The differential equation. So we're going to go y prime equals 1 over 2y. Right? There's my t. And this is my solution. So my solution gets plugged in to that. Right? Just like before, we took the 4 and we plugged it in to see if it really was a solution. So we're going to take that thing we think is a solution and plug it in there. Well, the right side's easier, so let's do it first. So in place of the y, we're going to put what? Square root x plus 4. Now, before we go any farther, I mean, you look at this, you say, gosh, how does that look like that would be the solution? Who knows, right? I mean, what in the world would that be the solution? I don't know. Just like an algebra kid, like, why is 4 a solution? Well, if you plug it in and the two sides are equal, then it's a solution. If they're not equal, it's not a solution. That's all we're doing. Okay, so this, I can't really do a whole lot more to this. I mean, I can, but let's wait and see what happens over here. Okay, so on this side, I want y prime. So what am I going to put there? No, and everybody always says that. Everybody always thinks that first. Y prime's 1 over 2y. We're going to put that there. No, you don't use your equation you're trying to solve. You use your solution. That's what you use. So right here, we want to put something for y prime. How are we going to do that? Let's do the derivative of that solution, right? So we need to do the derivative of this solution. So if y is going to be x plus 4 to the 1/2 power, that's how we better write it, right? So doing this verify, notice on the last one I did. When I did the verify in red here, I had to do the derivative. So doing this verify always involves doing a derivative. So to get y prime, I need to do the derivative of that. What do you get? 1/2. Inside always stays the same. And then it'd be the negative 1/2 power. That's y prime. That goes on this side. 1/2 x plus 4 to the negative 1/2. Now, are those two the same? Well, we can see they're the same, but we need to do it so that, like, we could pull in some 6th grader from down at Horizon and ask them if it was the same. It's got to look the same. They don't yet, so we need to keep going. So negative power means what? Flip it to the bottom, right? So this is going to flip to the bottom with that 2. And then it would be 1/2 power down there. But 1/2 power also means square root. Sure enough, it worked. It is the same. Right? So this is a solution to this. And notice it has an x in it, right? That's what we want. We want the original function f or y or whatever the output variable was up here. We don't want any derivatives in our solution. That's the differential equation. Okay, so we got to kind of, again, I like to compare it to what I said here. I like to compare it to our algebra equations, but our algebra equations always had numbers for answers. We got to get it through our head that the solution to a differential equation is another equation. It's the original equation without derivatives in it. So it's y equals or p equals or whatever the variable happens to be that we're using in that problem. Okay? All right, so I've just given you 2 examples of differential equations. Let's write those down. We really have 3 types that we're going to deal with. Okay? So let's write that down here. We will have 3 types, and you probably want to have this, somewhere in your notes that you can kind of see it, or it stands out a little bit. We will have 3 types of DE. Okay? The first type would be DEs that we can solve by antiderivative. These would be the simplest ones, like what we just did. Let me write down a few. Y prime equals 2x minus 7. Y prime equals 3. Y prime equals x squared plus sine x. What do you notice about every one of those? They have y prime, but they're all new because they're all differential equations. What else do you notice about it? They all have x in them, or just a constant. They all have x in them. So we can do the antiderivative with respect to x. So these we can solve by just doing an antiderivative. So if they just have x in them, then we're good. They're just basic kind of antiderivative type thing. Okay, the second type would be like the other one we just did. DEs that we can't solve. We haven't learned enough. We haven't taken a course in differential equations. We must be given the solution. Now later on in the year, we will learn how to solve a few types of differential equations later, much later, okay? But for right now, so let's put a few of those down, like y prime equals the one we just did. Y prime equals 1 over 2y. Or y prime equals 3x plus 2y minus 4y double prime. Right? You can even have double primes in there. And it doesn't even have to be y prime all by itself. It could have been, we could move stuff around. Like I could add this 4y double prime over here. I could have y prime plus 4y double prime equals 3x plus 2y. Whole mixture of x's and y's and other primes. We don't know how to do those. So we have to be given a solution. But for those problems, I could give you a y equals and say, is that the solution? And you could do a t-chart and verify. Okay? And then the third type, and we'll do an example of this one here in a second, are DEs, and there's only one for right now, where we will memorize the solution. In other words, it's such an important and such a prevalent differential equation. It's not one we know how to solve, like number one. It's more like number two, where we can't solve it. We're just going to memorize the difference, the solution. And here's the one we're going to do right here. If we have y prime equals k times y prime equals a constant times y, the solution to that is y equals a e to the kt. Y equal, then that's e is in e to the x, right? A e to the kt. T is our input there, not x. So instead of x, we're using t as our input. A lot of differential equations, since y primes are rates, a lot of differential equations are used for rates. And so t is a lot of times the input instead of x. T for time. So if we see a differential equation that looks like that last one, y prime equals k times y, then we just do that right there. All right, let's do an example of one of those. So if I had y prime equals 0.06 y, okay? Pacemaker. Okay. You may know CPR. Okay. Y prime equals 0.06y. Okay, this looks like that third one that we just wrote down, where the k is in place, replaced by 0.06. So what that means, as soon as we see that, we know immediately that the solution to that is what? A E 0.06t. Now, this example is compound interest, is what this example is. Interest, compound interest. Think about what this is saying. If Y is dollars in the bank, or invested, or what your investment's worth, and T is time in months, years, days, whatever. What this is saying right here is that Y prime, the rate your money grows, right? Because that's what Y prime is the rate of change. The rate your money is increasing, hopefully increasing. The rate your money is increasing is equal to 6% times how much money you have. Isn't that what interest is? You take 6% times the amount of money you have, and that's your interest. That's the amount your money's increasing. The rate that your money's increasing, right? In dollars per year or whatever. So it's a very simple little formula and it makes sense. It's some constant, the interest rate, times the amount of money you have. That's the amount of money per year that your money is growing, the rate that it's growing. Okay? Now, so the value of differential equations is there, like for engineers and so forth, that it's easy to describe real-world situations in the language of differential equations because they're usually talking about rates. So they're easy to write. Unfortunately, they don't give us much valuable information as equations. This describes what's happening to my money, but if I want to know how much money I have after 5 years, can I plug a 5 into this equation? No. It's not much value to do, for doing that. So it describes the situation really well, but it's not very valuable to tell me how much money I have. I need this equation to tell me how much money I have. I can plug a 5 into this equation if I know how much I started with, right? So I'd need to know what A is. So I'd have to give you some more information so you can find what A is. But, so the solution to the differential equation is more useful, but it's usually harder to write and harder to figure out. The differential equation is easier to write, but it's not as useful. So they write the differential equation, and then they use those techniques to turn it into the solution equation, which is then more useful. Yes. Let's look at that one. That's a great example. Thank you for mentioning that. That is on number 35. Boomtown, right? Now the only difference is I didn't, and what I didn't do is give it to you as a differential equation. That's exactly what it is. It's a P equation is the population. You just had to plug some numbers in. And then in part B it says at what rate was it changing, so you had to do the derivative, right? The P prime, because that would be the rate that it's going. Exactly. Now, as we do more with differential equations, I could have given it to you as this, and then had you go to here and so forth. But that's exactly what that question was about. So section 6, which is mostly about exponential functions, this is the most interesting example of exponential functions there is this compound interest and growth, exponential growth, and exponential decay, okay, which is a leveling off effect, okay? That is a very common use of exponential functions, okay? All right. So we'll come back. I'll after we do this other thing, I'll come back and throw one more problem up here, a verify kind of problem where we can work it through and look at it. Okay? And then again, you'll get a chance to practice. But that's what differential equations are about. Okay? So it's a new thing, and it's kind of hard to get your mind around a little bit. So we'll be working on that the next couple days. And I'll try to get very specific on what I want you to do. Your homework tonight is almost solely verify. So it's going to be this kind of stuff. Okay, it's going to be this kind of stuff, this T-chart kind of stuff. It's going to say, is this a solution to this differential equation? And you're going to be doing this kind of stuff. Okay, so that's the majority of what I want for today. Okay, the next thing is this right here. Okay, so let's do this. I want you to stand up for about 45 seconds and stretch and move about. Take a quick mental break.
He's like, hey, me and Granny just start class now. Well, so dressed up this morning, Service Academy nomination, Senator Fisher office, he was panel with us. So they're doing that interview. I'll show you the email.
All right, time's up. Time's up. Okay. All right, so shift of gears here a little bit. Now, you don't need to write any of this down just yet. I want to rehash a little bit of old stuff, and then I'll show you what we're going to write down. So the chart stuff in section 2.4 that we did, that was on this last quiz, with the local max min, increasing, decreasing kinds of questions. All right, so let's say we have a function f here. Now, usually we have it with an equation now. All right, so you had an f equation. We want to find the local max, local min. Well, those happen when what? When f prime is 0, right? And then you got to see if f prime changes from positive to negative and so forth, so you do the number line, right? So we do the derivative, we set it equal to 0, we solve it. In this case, it'd be at 2, at 4, and at 6, right? And so you solve your equation, you do yourself a number line. I put zeros here, you don't have to put those there. And then you check in between. And you pick some numbers, right? You plug those into the f prime equation, right? The f prime equation, because you're trying to see if f prime is positive, negative, and so forth. And then you can tell you have a local max, local min, local max, as you can see here in the picture. Okay? And then, now what we haven't done is the inflection points. If you want to know where the inflection points are, then you want to see where f double prime is 0. So, and we will do that as the week goes on. I don't think we're going to do any of that here yet today. But you would take the second derivative and set it equal to 0, do a number line for it, and then what's this mean if f double prime is negative? What's that mean about f? Concave down. Concave up, concave down. So that means at 3 and 5, you would have inflection points, since f double prime changes concavity. So it's really the same thing. So doing concavity and inflection points is really the same thing as doing increasing, decreasing with f prime. Okay? So that's chart stuff. Now, what we want to do is transition over to this idea of global max min. And we've talked about that. What's that mean, global max min? Highest point, lowest point. Now, we're going to stick right now with nice, smooth curves. No sharp points. No breaks and gaps like our quiz had when we were doing limits and stuff. None of that. Nice and smooth and curved things. So if that's the case, where could the highest point possibly be? Where's the highest point on this one? At the local max. Wouldn't it have to be somewhere where the derivative is 0? What about the lowest point? Where's the lowest point on this one? Is the derivative 0 there? No. But so what about 7? 7's the end point of the interval, right? It could happen at an end point, right? In other words, I mean, think about a curve, and we usually will have a set interval we're looking at, okay? So here we're only looking from 1 to 7. So the highest point is here, where the derivative is 0. Now the derivative is also 0 over here, but it's not as high as this one, so we don't care about this one. When we were doing local max min, we cared about both of them, right? We wanted both those as local maxes, and we wanted this one as local min. And we didn't care about endpoints when we were doing local max min, right? Just when the derivative was 0. But global max min, we want the highest point and the lowest point. So the key is we just got to know where to look. We can't just start plugging points into the f function, see what the values are. We got to narrow it down. Well, the only, I think, and think about this a minute, the only place it could be is at a peak, which would be when the slope is 0, right? Because we're not going to have any sharp points or anything. So it got to be at a peak where the slope is 0, or it could be at an endpoint, right? Like I could have had this graph come back up and be up here, right? And then the highest point could have been at the left edge. And the lowest point could have been at the right edge, right? But I don't think there's any other place it could be. So what we're going to do is we're going to call those candidates. Because remember, we're asking a different question. We're not asking for the local max min. We're asking what is the global max and min value of the function? What's the highest output, lowest output? Okay? So what we're going to do is we're going to identify these candidates. Now we'll write this down in a second here. We're going to identify our candidates. The only places the high and low spots can be is when the derivative is 0, which we already know how to find that, or at the endpoints. That's it. So it'll look something like this. So we'll figure out where derivative is 0, which in this problem is 2, 4, and 6. We'll locate our endpoints, which are usually given to you in the problem. And then we're going to do what LOC, list of candidates. We're going to take all of these values and we're going to plug them into where? The original f function, not f prime like we did on the chart. On the chart we plugged into f prime because we wanted to know if f prime was positive or negative for increasing and decreasing. That's not what we care about here. What we care about on a global max min problem is we just care what f's outputs are. So we're going to take all of our possible places where the high and low spots might be. We're going to plug those into the f function, and the highest one will be our max, and the lowest output will be our min. And usually we want the y value. You know, on local max min, you usually wrote the x value. Local max is at x equals 2. Local min's at x equals 1. For global max min, we want the value, the output. And we'll write that down. So let's do an example. Let's do an example. So we're going to do as our example here. Well, no, let's write some notes here first, and then we'll do our example. So, first thing we want to do is we want to identify our candidates. Okay? Our candidates are places where the max min might occur are 1, where f prime is 0, meaning stationary points, or 2, they might be at endpoints. Okay, that's the only place they can be. So we're going to find those points. So we're going to find where f prime is 0, the endpoints are usually given to us, and we're going to plug those into the original function using a list of candidates, and that's going to be our global max and our global min. That's it. That's the only place they can be. All right. So let's do problem 37. This is like one of your homework problems that you're going to have. It's a piece of the problem, actually. This is on 37 on page 147. It's a trig one. So this will give us some trig practice right along the way here. I think that's the function, isn't it? On 37. Did I have the right page, 147? Okay. This function, now this would all be no calculator. Now the directions actually say quite a bit. The directions say, draw a graph of the function. We're not going to do that. Okay? We're not going to worry about that because we got graphing calculators. I mean, there was a time we used to do a whole big unit on sketching a graph of this by hand. And we took all this information we're going to be finding, and we plotted some points, and we did these extensive graphs. Well, that was kind of in the days before graphing calculators. Now that we have graphing calculators, being able to graph these things by hand is not that useful a skill. So we've kind of eliminated that and went on to do some other things. Okay, so we're not going to worry so much about drawing the graph. But they want us to label the local max and min. Local extrema means local max min. We'll get to that in a second. Global max min, that's what we're going to do right now. And then the inflection points, which means we have to do the second derivative. Okay? It says use exact values rather than decimal approximations, which is their code for saying no calculate. No calculate. All right, so we're going to focus on global max min for this one. All right, so this is some graph. We want to know, and we're looking at it from 0 to 2 pi. 0 to 2 pi. All right, and we want to see where's its highest point and where's its lowest point in that interval. Well, there's two places it could happen, at the endpoints or at the stationary points. So let's do the stationary points first. So let's do the derivative. All right, what's the derivative? 1/2 plus cosine x, and we set that equal to 0. There are a few people in the quiz yesterday that did not set their equation equal to 0. You've got to do that. When you're solving the equation, you have to put it on your paper what you're solving. Okay, you have to have equal 0 there. Okay, and then we can subtract a half from both sides. Where does cosine equal -1/2? Well, now we got to think about our unit circle. Cosine, that'd be over in these two quadrants, right? And isn't that a pi thirds reference? So I think it's up here at 2 pi thirds. And down here, 4 pi thirds, right? Cosine's negative in these two quadrants. So it's x equals, and since we're limited from 0 to 2 pi, that's all we need. So 2 pi thirds 4 pi thirds. Okay, now I've got some videos with some trig review and some of these max min problems worked out that I'll show you where they're at on the website here in a little bit. Okay, but we're going to have to be able to do this. One of the things that will for sure be on the next quiz will be some of this no calculator trig stuff, where you've got to know kind of the unit circle a little bit. All right, now there you go. There's your stationary points right there. Now so far this is no different than what we would have been doing for our last quiz. Right? Very much the same. Do the derivative, set equals 0. Now, if this would have been chart stuff, if this would have been local max min, what would we do next? Number line. We're not going to do that. We'd have made a number line now, put 2 pi thirds, 4 pi thirds on it, right? And we would have picked points in between, plugged it into f prime, and we'd have found increasing, decreasing, that stuff. That's local max min, which we still need to probably do for 37. That's what they said. So on your homework, you'll do that. But that's a separate part of the problem, okay? So now what we're doing is we're just finding our candidates, okay? So we have those candidates, and then, of course, we have our endpoints, right? Our endpoints are x equals 0 and x equals 2 pi, right? So the possible places where the highest point and the lowest point could be are at those 4 places. So what do we do next? LOC, our list of candidates. And we're just going to plug them into the f function. So just as a reminder, I'm gonna write it out. F of 0. Now on the AP test, I'm going to put them in order here. So go f of 0, f of 2 pi thirds, f of 4 pi thirds, and then f of 2 pi. Okay? But on the AP test, you have to justify that something's a global max min. A list of candidates is a pretty good way to do it. It's accepted, and it shows your work, shows you know what you're looking for, and so forth. All right, so now we have to plug those in. Now, sometimes on the no calculator, this is the hardest part, because now we've got to find these values. But the key is we go back to the original here now, not f prime, which is different when you're doing the number line stuff. All right, so we put a 0 in here. 1/2 times 0 is 0. What's sine of 0? Sine of 0 would be the y value right there. So 0, right? Now we're going to put in 2 pi thirds. 1/2 times 2 pi thirds. What's 1/2 times 2 pi thirds? 2's cancel. Pi thirds. Just write it down for now. We'll deal with it here in a minute. Plus, and then what's sine of 2 pi thirds? Sine of, let's see, this was negative 1/2 was the x coordinate. That was cosine. Is it root 3 over 2? Isn't it root 3 over 2 would be the sine? So sine of 2 pi thirds is root 3 over 2. Okay? What about 4 pi thirds? Well, let's plug that in. We got 1/2 times 4 pi thirds. What's that? 2 pi thirds? Plus, and then what's the sine of 4 pi thirds? It'd be negative though, right? Because it's a y value here in the unit circle, so it'd be negative root 3 over 2. Now, if you mess up these values on the unit circle somehow, remember we talked a little bit about partial credit. If you do the derivative set equals 0, if you mess those points up, if you continue on and take your points and you do a list of candidates and you plug them in and you get, you can still get a lot of the points here, even if you mess up some of the trivia. All right, so keep going. All right, now let's put in 2 pi. So 1/2 times 2 pi, that'd be pi. And then what's sine of 2 pi? That's back to 0, right? So that's 0, so it's just pi. All right, now, what we're interested in is which one of those y values is the biggest and which one's the littlest. So let's do this. I'll do this in red. Okay, let's look at this. What's pi? 3, roughly 3. So 3 divided by 3 is about 1. That's usually as accurate as you need to be here. What's root 3, roughly? Root 2 is 1.4. Root about 1.7 or so, because root 4 is 2, and root 2 is 1.4, so it's got to be in between. It's about 1.7, 1.8. Let's call it 1.8, make it easier. 1.8 divided by 2 is about 0.9, so 1 plus 0.9, so that's about 1.9. That's about as accurate as you probably need to be. Okay, otherwise it'd be a calculator problem. But yeah, you might have to do this. 2 pi thirds, so 2 pi is about 6. 6 divided by 3 is about 2. We said this was about 0.9, but it's negative. So 2 take away 0.9 is about 1.1, right? And then pi, of course, is about 3. So the biggest one looks like is here. So usually what we do is we just circle that and say max. Because again, we care about the y value here. What's the global max value? So the max value seems to be pi, and it looks like the littlest value is back here at the left end. The min is 0. So I just found the global max min, and I justified that those are the highest and lowest points because of all my work here. I got my candidates, I did a list of candidates. That's a global max min problem. So I'll put this on the website here. I'll put up, under today's thing, I've got this comparison of chart versus global max min. A chart problem looks like this, a global max min problem looks like this. Okay? Now, if we were to continue on 37, let's just real quickly here. On 37, it also asks for local max min. Well, you already did the work of finding the stationary points, right? You already had that. It was 2 pi thirds and 4 pi thirds. So we would do our number line. Okay, you don't need to write this down. You don't want to. It's up to you. But so this would be just like what we did on the last quiz, except the last quiz we did polynomials. We could do the same thing with trig. So we found our stationary points. So we need to pick a number. And what was f prime? It was 1/2 plus cosine x, right? Okay. So what's a number before 2 pi thirds? Here was 2 pi thirds, 4 pi thirds. What's a number before 2 pi thirds? Pi thirds, okay? Pi thirds, sure. What's a number between 2 pi thirds and 4 pi thirds? 3 pi thirds, pi. Number over here? 5 pi thirds would be fine. Now there might be some easier ones to do, like we could have done pi halves maybe, or 3 pi halves. Those might have been easier plugging, but look, these aren't bad. It's up to you. It depends how confident you feel plugging them in. But I like those values because we're going to have to plug them into cosine. So what do we got here? Let's put in pi thirds. What's cosine of pi thirds? Cosine of pi thirds. It's 1/2, right? Remember, 2 pi thirds was negative 1/2, right? So cosine of pi thirds is 1/2. 1/2 plus 1/2? Positive. Let's put in pi. What's cosine of pi over here? Negative 1. 1/2 plus negative 1 is negative. 5 pi thirds down here. Cosine, that's 1/2 again. 1/2 plus 1/2, positive. So there's all your local max min information right there. And you could write that down then and show your justifications just like we did on the quiz yesterday. So local max there, local min there, it's increasing to there, decreasing to there, increasing to there, and so forth. And if we had to do point of inflection, I'm going to say for today, let's don't worry about inflection points. We would just do the second derivative and do this all over again. So a lot of stuff. So on the quiz, you wouldn't have a problem as big as 37 where we had all that to do. I'd break it into separate problems. You know, one would be a global max min problem, one would be a local max min problem, one would be an inflection point problem, and so forth. Okay? Kind of break it up. All right, so those are the two main things I wanted to go through. Those are really the two new things. Like I said, the chart stuff, we just kind of did that a little bit with the trig, with the chart and local max min, and then kind of the derivative rules, and those kind of fit in there. We just did some derivatives when we were doing the verifying. We did some derivatives when we were just doing our max min problems, a little bit of antiderivative in there. And so that's really it. I mean, we've kind of hit it, but now you guys need to get in and be able to practice some and so forth. So let's do this. Let me throw one more problem at you. And then go through what your homework is with you a little bit. Let's go back to the verify and let's have you try this. We'll do two quick ones with differential equations. Here's your differential equation. Here's your differential equation. Okay, so the first equation there is your differential equation. Is that next one a solution to that? So this is where you'd want to do the T-chart to check. Okay, so is this what you have for your t? What are you getting, yes or no? Anybody got that? Are we stuck? Okay, so our setup, everybody's set up okay, like this, right? You take the differential equation, and into this we have to plug in stuff. Now, what are we going to plug in for y? X cubed plus 2x is going to go in for y. What's going to go in for y double prime? Right? Y prime would be 3x squared plus 2. Y double prime is 6x. So 6x will go in here. So I could work with this. This would be x cubed minus 4x. Right? Plus 2x minus 6x. And then there's nothing more I can do with that. So what's going to go in here for y prime? 3x squared plus 2. And what goes in for 2x? 2x, right? 2x. Can you combine anything? No. Are the two sides equal? No. Not a solution. There you go. Not a solution. The two sides were not equal. Okay? So that's what that looks like. All right. Last one. Y prime equals x squared. Let's make it be 3x squared. We'll make it easy. Plus x and y of 0 equals 1. Solve the IVP. The look on your faces was kind of funny. IVP, what the world's an IVP? IVP is initial value problem. Initial value problem. An initial value problem is a differential equation plus an initial condition. Remember when we gave you f prime graphs and told you to draw f? What happened when you went to draw f? You didn't know where to start. But if I told you 1 point on the original graph, then you would know where to start. That was an initial value problem. So here's the differential equation. I'm telling you 1 point on the original function. Okay? This is called an initial value problem. A differential equation with an initial condition. So when I say solve the IVP, I'm really saying solve the differential equation. When you solve a differential equation, the solution is what? The original equation, right? What you're trying to find is the original equation, which in this case would be labeled y. Y equals. That's what you, okay, go. Go. Because this is the first type, the type we can solve. Because it has all x's in it here. See? So talk about it with your neighbor if you're not sure what to do. We've actually done it already today, but I know we've done a lot today. So I gave you y prime, and I'm asking you for y. Right? Duh, right? I gave you y prime, I'm asking you for y, right? Solve, I'm asking for the original function, okay? All right, so to start, what are you doing? All you're doing is the antiderivative, right? This is type 1, the one we said that if it's got all x's in there, it's y prime. You're trying to find y. Remember, solving a differential equation means find the original function, in this case y. The way you go from y prime to y is you do the antiderivative. All right? That's it. That's it.
That's it?
Say that again. Okay, well, I'm sorry. By that's it, I don't mean that's it, we're done. I mean, that's it as far as all you need to do to go from y prime to y, right? Now, there's many other types where we can't solve them, right? So I can't even ask you to solve. All I do is ask you to verify the solution, which is like the one before. I just said, hey, is this the solution? Because we didn't know how to solve that. But this one we do know how to solve. It's just a simple antiderivative. Okay, so this is step 1. And a lot of times that's your only step. If I didn't give you this, remember when we did the graphs, right? You didn't know where to start. There was a whole bunch of them, vertical shift. Remember the plus C, that's what that is. But if I give you a place to start, you should be able to figure out C, right? So what did you do from here? You went ahead and plugged it in. So that's why I gave you that initial condition, is so you can find C. So you plug a 0 in for x, here, here, and you put what in for what? 1, right? The output. So you put a 0 in for x, you put a 1 in for y, and of course this is a pretty easy one. You just get C is 1. It's not always going to be that way that C is 1. It just happened to work out when we put in 0, everything else dropped out. C becomes 1, and so your actual solution then is that. And that would be that specific graph. And actually those are the names. This is called the general solution to the differential equation. This is called the specific. Not a big deal right now, you know that. But this is the specific solution to the differential equation. This is the general solution to the differential equation. Okay? And then sometimes a problem like this could be taken just one step farther. A lot of times they'll say solve the differential equation or solve the initial value problem. And then they'll say, and then find y, and then find y of 2. Well, that's easy. Once you've done all this and you find your y equation, we can now plug in a 2, and we can find y of 2. Okay? 2 cubed would be 8, 2 squared is 4, times 2 is 2, 8 plus 2 is 10, plus 1 is 11. And so we could find y of 2. That'd be kind of the equivalent of the bank interest problem. I'd give you the bank interest equation, like the 6% interest. And then I give you an initial condition, which would be like how much money you put in at the beginning. And then I ask you, how much money do you have 10 years later? Right? That's kind of what that problem would be like right there. All right. So, problems for you to work on. And like I said, I'll be here in the morning, lunch, whatever. We got to work pretty hard the next several days, this weekend, probably into, through Monday and so forth, to try to kind of get this stuff all clarified. There's not going to be a lot new, really, between now and Tuesday. It's going to be more a matter of practicing, clarifying. We're going to maybe do some inflection point examples with the number line, but that should be fairly similar to what we've been doing. Got practice up on our trig. I was going to show you, I've got just enough time to show you on the website here, but let's get this. So this is the section right under the solving the equation review sheet on your assignment sheet. I changed it just a little bit. On 3 through 6, let's just do 6. Let's add on 43. On 47, I've changed the equation to this, or I've not changed the equation, I've given that to you. That was the one we're supposed to memorize. On problem 47, it's a bank interest problem. They give you the differential equation, and then this is the solution. This is the actual equation you'll use in the problem. Okay? And you can find it right in your notes. We talked about that in the notes, but I just put that up there for you. Now, 39 and 44 probably take the longest, to be honest, of those. Those are like the 37 we did, the global max min. You can do the global max min part on 39, do the local max min part. You can skip the point of inflection part, the one that needs a second derivative. Then 44 just asks you some questions. It's, again, a number line problem and kind of a global max min kind of problem, list of candidates. So that's going to be in there. Okay? All right. Since there's really not time to get started, let me show you a couple of things that are on the website that could come in handy here over the weekend or whatever as we get ready, as we get into this. Over here under class videos, the daily videos have all been under chapter 2. Okay, but I have a couple others here. One says max min inflection point review videos. And I've got several of them here where I just worked problems out under a document camera. They're only 5-6 minutes long. Okay, here's a global max min problem with a polynomial example. Here's a local max min problem. Here's a local max min with trig. Here's an inflection point with trig, no calculator. And then here's solving an initial value problem, a differential equation. So those might be ones, like I said, they're 2, 3, 4, 5 minutes long is all. And then I've also got a trig review. This is from class last year. It's probably 45 minutes long, just going through some trig review, unit circle stuff. And there's also a unit circle. I'll post it in today's class notes. A unit circle again if you want to review that. Okay. All righty.